Hello, everyone, and welcome to our webinar on levels of measurement. And just before we get started with the webinar, I'd like to present this information in case you are interested in additional support outside of the webinar. So we are a full service dissertation consulting company, so we assist with all aspects of the dissertation. So if you are interested in any help or support outside of this webinar, you can use this information to contact us and find out more about the types of services or assistance that we can provide. Okay, so I'll start with just an overview of what we will be discussing in the webinar today. So we'll be talking about levels of measurement, and we'll start off by talking about why levels of measurement are important and what levels of measurement are. And then we'll go through and define the basic levels of measurement, which include ratio, interval, ordinal, and nominal. And then we'll go through how to determine appropriate quantitative analyses to conduct based on levels of measurement. And then finally, at the end, we'll have time for questions. So if you do have any questions during the presentation, you may put those into the question section. And any questions that aren't answered just during the course of the presentation, at the very end of the presentation, we can go through and answer some of your questions. So let's first talk about what exactly are levels of measurement and why they are important to our research. So levels of measurement are the properties of the values or categories that appear in data. So for instance, let's say you have collected data for a certain variable and all of the values for that variable are just ones and zeros. Well, without knowing exactly what the level of measurement is for that variable, we may not really know exactly what those values for ones and zeros refer to. Are they just continuous numeric values? Do they represent categories? Without really knowing the level of measurement, it's hard for us to determine how we can analyze or interpret those values. So what levels of measurement do is they help us determine the most appropriate ways to describe, analyze, and interpret data. So if we know exactly what those values in the data represent and how we can interpret those values, we can determine the most appropriate way to analyze those values. And there are four basic levels of measurement that are used typically in the realm of the social sciences and at the level of dissertation research. And those are ratio, interval, ordinal, and nominal. However, it is worth noting that there are other classifications beyond these four basic levels. And there's, actually a body of literature that debates what the most appropriate classification is in terms of the levels of measurement. However, these four basic levels represent the most useful classification in terms of doing dissertation level work in the social sciences generally. But it is worth noting that there are other types of classifications. For instance, there are certain classifications that distinguish interval or ratio and interval data from count data and other examples. So although these four basic classifications will serve you well for the most part, it is possible that data may need consideration beyond the four basic levels, depending on exactly what type of data you're looking at and what the scope of your study is. So now let's start talking about the different types of levels of measurement and what they are. We'll start with ratio and interval data. So ratio and interval measures represent continuous numerical values. So if you think of, for instance, just numbers on a number line, like numbers between 1 and 10 or something, that has just a continuous numeric value, like someone's age in years, their income in dollars. That's what we think of when we think of ratio and interval type data. There's a fine distinction between ratio and interval, although they are very similar. So for ratio data, the numeric values have a non-arbitrary or meaningful 0 point. So for instance, if you take something like income in dollars, $0 means that there is a complete absence of income. Their income is 0. And the same thing with something like a count. So if you look at something like a count of the number of times per day that someone checks social media, if they report 0 times per day, it means that there's the complete absence of that behavior. So for ratio data, there is a non-arbitrary and meaningful 0 point. When we get up to interval data, it's very similar to ratio, but for interval data, the 0 point may be arbitrary or not meaningful. For instance, if you take something like temperature in Celsius or Fahrenheit, 0 degrees does not mean a complete absence of temperature. The 0 point for temperature and the Celsius and Fahrenheit scales is arbitrary. And the same also applies to something like dates or years. So for instance, if you look at years, the year 0 AD does not represent the absolute beginning of time. It's an arbitrary 0 point. And so that's kind of the fine distinction between ratio and interval data. But the most important thing to consider with both ratio and interval data is that the degree of difference between values is known and consistent. So if you have numerical values, just on a number line, counting up from 1, 2, 3, 4, etc., we know that the degree of difference we know the degree of difference between those values, and we know that that difference is consistent across all of the values in the data. So for instance, we know what the difference is between a value of 1 and a value of 2. And we know that that difference is also the same between a value of 2 and a value of 3, and so on. And because we know that the degree of difference between values is consistent, we can apply certain mathematical operations in terms of interpreting these values. So for ratio, you can pretty much use any mathematical operation in interpretation. For interval, you can use simple addition and subtraction, but not necessarily multiplication or division. But what exactly do I mean by this? So for instance, if we look at ratio data and we look at something like income in dollars, you can apply meaningful mathematical operations to your interpretation such that someone who makes $10,000 a year makes half as much as someone who makes $20,000 a year. Someone who makes $40,000 a year makes 4 times as much as someone who makes $10,000 a year. So you can apply those types of mathematical operations to your interpretation of the values. So next, let's talk about the more categorical levels of measurement. So interval and ratio are more the numeric levels of measurement, and ordinal is a categorical level of measurement, where ordinal measures represent categories that can be ranked or ordered. So for instance, from lowest to highest or from highest to lowest. So some good examples of this would be something like education, where you may have just categories of someone's level of education. So you might have high school, college, graduate school, things like that, where we know kind of the order in terms of what's a higher level of education. We know that college is the higher level of education than high school, and we know that graduate school is a higher level of education than college. Other examples may be things like letter grade, So we know that an A is higher than a B, and a B is higher than a C, and so on. And this also applies to things like Likert items. So for instance, and we'll talk more about Likert items specifically in more detail a little bit later. But this would be things like where if someone rates an attitude or behavior from strongly disagree to strongly agree. I mean, we know that strongly agree is higher than strongly disagree. So again, these are categories that we can put in a specific order from lowest to highest. But the issue with ordinal data is that the degree of difference between categories is unknown and or inconsistent. So for example, take something like education, where we have the three groups: high school, college, and graduate school. Even if you were to assign numerical values to these categories, for instance, you can assign a 1 to high school, a 2 to college, and a 3 to graduate school. We don't necessarily know how much more of an education someone has being in college compared to high school, and being in graduate school compared to college necessarily. So we can't apply mathematical operations to our interpretations of those values. So even if we assign a 1, a 2, and a 3 to high school, college, and graduate school respectively, we can't say that someone in college has twice as much of an education as someone in high school, or that someone in graduate school has 3 times as much of an education as someone in high school. So because we don't know what the degree of difference is between the categories, we only know the order in which we can rank them. We can't apply those basic mathematical operations to our interpretation. So finally, let's discuss nominal levels of measurement. So nominal measures represent categories that we cannot put in a certain ranking or order. So these would be things like gender. So, I mean, gender is a very simple example. We may have male, female, or other categories of gender, but we can't put those in any kind of meaningful order from lowest to highest. So we can't say that females are higher than males or vice versa. The same thing would apply to something like race or ethnicity. Things like location, region, or someone's nationality, or what country someone's from. And things like occupation or specialty. So if you have a wide range of occupations like nurse, teacher, doctor, office worker, we can't really put those things in any kind of meaningful order from lowest to highest. They're just completely separate categories. And so with nominal data, the categories cannot be meaningfully ordered, and the degrees of difference between the categories cannot be determined, similar to ordinal data. And therefore, we can't apply any sort of mathematical operations to our interpretation of those categories or values associated with those categories. And now, like I said before, let's look a little bit in more detail about specifically Likert type scales, because these are used very often in dissertation level research in the social sciences. So if you're doing a survey study, many survey instruments use Likert type responses. And you may already be familiar with what a Likert scale or a Likert response is, but if you're not, Likert items are basically ways that we can measure attitudes and behaviors on a numeric scale. So we might present someone with an item and then ask them to rate the extent that they agree or disagree with the statement using a scale like the one we see here. So a basic example would be a 1 to 5 scale that varies from strongly disagree to strongly agree. And we see that we have disagree, neutral, and agree as points in the middle of those. So these are used very often in, like I said, social sciences and dissertation level research. And you may see instruments that don't just use one single Likert item to measure something, but rather they use multiple Likert items to measure a single variable or construct or concept. So for instance, if you have something like, the Rosenberg self-esteem scale, or the Beck anxiety inventory, or some kind of measure of self-efficacy, often these measures will not just have a single Likert item that measures that behavior, but rather it may be done across multiple Likert items. So you may have like 10 items and they each use a Likert scale response. So for instance, you might have 10 items that measure self-esteem in your survey instrument. So the question then becomes, when you deal with these types of items, what exactly is the level of measurement? And there's a lot of debate about this in the statistics literature, and a lot of people will have different views on how we should treat this data. And this may even come down to your specific committee members or reviewers' opinions on how they want you to treat this type of data. But we can tell you here what the most typical way to treat these variables is. And that is, if you're looking at a single Likert item, just one single item that has a Likert type response, we will typically treat this type of data as ordinal. However, if you're taking multiple Likert items, like for example, like a 10 item self-esteem scale, if you're taking multiple items and you're summing or compositing them together into a single score for self-esteem, then we will typically treat that composite score as interval. So that's a very important distinction in terms of the types of analyses that are appropriate for interval and ordinal data, respectively. Like I said, there's a lot of debate in the statistics literature over the most appropriate way to treat these items, but treating single Likert items as ordinal and composite scores as interval is the most typical way you see these types of measures treated in this level of research. So now that we've talked about the different levels of measurement, we have a general sense of what they are. Now let's talk about how we pick the most appropriate analyses depending on the level of measurement of our variables. So let's start off with descriptive statistics. And descriptive statistics may seem really straightforward, but it actually is very important that you choose the appropriate types of descriptive statistics based on the level of measurement. So for variables that are on a ratio or interval level of measurement, you will want to report things like the mean, the standard deviation. You can also report the median, mode, minimum and maximum values, and things like skewness and kurtosis. So you have all of those options available to you when you're looking at ratio and interval data. When you get into the categorical levels of measurement, like ordinal and nominal, your options for meaningful descriptive statistics are more limited. So generally for categorical type variables, you will want to report frequencies, which is just the number of observations you have for each category, as well as the percentages associated with those frequencies. So the percentage of people in your sample that fit into a certain category. Specifically for the ordinal level of measurement, you can also report the median or the middle value, because we do, for ordinal data, we are able to rank the values in a certain order. So we are able to determine the middle value for ordinal data. You can also report the mode, which is the most frequent response or the most frequent category, as well as the minimum and the maximum, because again, with ordinal data, we can rank them in order from lowest to highest. So we know what the lowest possible category is, and we know what the highest possible category is. However, for nominal, you're much more limited. You're basically limited to just frequencies, and in some cases, you can report the mode or the most frequent category that appears in the data. So now let's go over the more complicated types of analyses and what is appropriate depending on the level of measurement. And this will generally be dictated by the level of measurement of your dependent or outcome variable. So what are the types of analyses we can do when our dependent variable or our outcome variable is a ratio or interval level of measurement? In these cases, we can use most parametric inferential statistics tests. So we can use, for instance, things like t-tests and ANOVAs to compare groups or repeated measurements of a variable. If we want to look at correlations or relationships or associations between two variables, we can use Pearson correlations if those two variables are both at least a ratio or an interval level of measurement. And then if we want to do an analysis with prediction, so if we want to predict a ratio or interval level outcome, then we can use a linear regression. And for a linear regression, our predictors or independent variables can be essentially any level of measurement. But what can we do when our dependent variable is ordinal? Generally, once we get into ordinal level data, we have to switch our analysis from parametric to non-parametric. So for instance, if we're looking at differences between groups, we will have to use non-parametric difference tests. So for instance, the Mann-Whitney test is the non-parametric version of the independent samples t-test. The Kruskal-Wallis test is the non-parametric version of a one-way ANOVA. The Wilcoxon test is the non-parametric version of the paired samples t-test, and the Friedman test is the non-parametric version of a repeated measures ANOVA. So these will accomplish the same things as a parametric t-test or an ANOVA will, but they are the non-parametric version of the test and may be appropriately used when the outcome or dependent variable is an ordinal level of measurement. If you're looking at relationships between variables, you have to go from a Pearson correlation to a Spearman correlation when the level of measurement is ordinal. It's also worth noting that for any of these non-parametric tests, like non-parametric difference tests and Spearman correlations, these can also be used with interval and ratio data. For instance, if certain assumptions of those tests are violated, you may use a non-parametric test to account for violations of those assumptions. So you can use these tests with ratio and interval data as well. But if you are looking at an ordinal dependent variable or outcome, then you will have to use these tests as opposed to their parametric versions. And so again, with Spearman correlations, as long as both variables that you're trying to correlate with each other are at least an ordinal level of measurement, you can use the Spearman correlation. And then finally, if you are looking at prediction, so if you need to do a regression, then if your outcome variable is ordinal, you can use an ordinal logistic regression. And again, in a regression, the predictors or independent variables can be any level of measurement. And then finally, what do we do when the dependent variable is nominal? Well, again, like we saw with the descriptive statistics, we get more and more limited as we get into nominal level data. So if we want to look at differences or associations between nominal level data, then we have to use something like chi-square tests, which are basically comparisons of contingent frequencies between the variables in the different categories. So an example of this would be if you wanted to see an association between gender and a diagnosis of depression. So was someone diagnosed with depression or not, yes or no? Since those are both nominal categorical variables, you might use something like a chi-square test to see if there's an association between gender and the diagnosis. So are males diagnosed more frequently than females or vice versa? If you need to do something more than just a simple relationship between two variables, and your outcome or dependent variable is nominal, then you probably need to use something like a logistic regression, so a binary or a multinomial logistic regression. So this can be used if your outcome variable is nominal. And again, you can use predictors or independent variables that are any level of measurement. And really the difference between the binary and the multinomial logistic regression is that the binary logistic regression is used if your outcome variable is specifically only two categories. And the multinomial logistic regression is used if you have a nominal variable that has more than two categories. And just as a note, if you still need more help in terms of determining appropriate analyses based on exactly what your research questions involve and what the levels of measurement are for your variables, we actually in our intellective statistics software have a decision tree that you can use. So I'll just show this example here where if you use our intellective statistics software, we have this decision tree feature where it'll ask you questions about the types of data that you have, and it'll offer you suggestions for what the most appropriate type of analysis is based on what your research questions involve and what the level of measurement involves. So you can see here that we have different options for analyses if the variables are scale or nominal or ordinal for certain analyses and so on. So you can use this feature in our software to get a better sense of what analyses are most appropriate and are available to you depending on what the level of measurement is for your variables. And that brings us to the end of the presentation. So again, if you are interested in additional support outside of this webinar, you can use the information that we have presented here to get in touch with us and learn more about the services and assistance that we provide. But otherwise, I'll go ahead and see if we have any questions that you may have. So again, feel free to, if you do have questions, go ahead and type those questions into the question section. Okay, so let's see what we have here. So first question I see is, military ranks, pay grades can be classified as categories or designated as O1, O2, O3, O4, O5, etc. Would the first example be categorical and the second example be interval? I think in this case, the first example, so if you have like different grades within the military, so like which grade is higher than another, then that would be ordinal level, because you have distinct categories. You may not be able to quantify the exact difference between the grades or the levels, but which one is higher than another. So in that case, I would treat that data as ordinal. And even if you can just designate them as something like O1, O2, O3, etc., if you don't know precisely what the numeric differences are between the categories, or if the difference between the categories is consistent between those different grades or levels, then that data would be most appropriately seen as ordinal rather than interval. Okay, the next question I have is, if my data set has nominal variables, ratio variables, etc., what kind of correlation test should I apply? Pearson correlation or Spearman correlation? So specifically, it depends on what the levels of measurement are for the variables that you are correlating together for any given correlation. So if you have two variables and both are either ratio or interval, then you can use the Pearson correlation. If any of the variables are ordinal, or if both of the variables are ordinal, then you would have to use the Spearman correlation. If any of the variables are nominal, then you would have to use something like a chi-square analysis. And then, can we see the ordinal slide again? Yes, I'll go ahead and click back to that one so you can look at that. And the next question is, if I have an outcome dependent variable that is ordinal, 3 categories, such as level of severity of an injury, what type of regression would I use? In that case, I would use the ordinal logistic regression if you have 3 categories and they're ordered like high, moderate, and low. And the next question is, if I want to measure the correlation, do I first do linear regression and then use the Pearson or Spearman? Not necessarily. It really depends on exactly what your research question is and what you're trying to determine. So really the difference between regression and correlation is that a correlation is just between 2 variables at a time, whereas a regression can look at the association of multiple predictors with a single outcome. So if you're just trying to see a simple bivariate association between 2 variables, you might use something like a Pearson or a Spearman correlation. If you want to look at how multiple independent variables predict a certain outcome variable, then that's when you would do a regression. So the next question is, I have 2 Likert scales and a dependent variable. I guess you're asking what test to use. So again, this will mostly depend on the exact level of measurement of your dependent variable. The level of measurement of the dependent variable is really what drives the choice of analysis in most cases. So if your dependent variable, or in other words, the outcome that you are trying to look at, is an interval or ratio level of measurement, and we can go back to our slides here. So again, when we have a ratio or interval level of measurement for our dependent variable, we can use t-tests, ANOVAs, Pearson correlations, or linear regression. And in terms of the Likert scales, if we go back to our discussion of should Likert scales be considered interval or ordinal, again, the most common treatment of those variables is that if you have just a single Likert item, so just one item that someone rated on a 5-point scale, then you would treat that variable as ordinal. However, if you're taking multiple Likert items, so for instance, if you had an instrument that has 10 Likert questions and composite or add up the responses to those 10 questions to get a score for that instrument, we would treat that composite score as interval in most cases. And so if we look at, again, a ratio or interval level dependent variable, these are the tests you can use, things like t-tests, ANOVAs, Pearson correlations, linear regression. If the dependent variable is ordinal, so for instance, if your dependent variable was just a single Likert item, then you would move into your non-parametric tests. So things like Mann-Whitney, Kruskal-Wallis, Wilcoxon, Friedman, Spearman correlations, or an ordinal logistic regression. It looks like those were all of the open questions that I had so far. But I'll just give another minute or two, see if anyone else has any additional questions. So if you do have any further questions, go ahead and type those in now. Okay, it doesn't look like I'm getting any more questions coming in. So I'll go ahead and, or hold on, looks like we do have one more question. So the question is, if two groups appear to be unevenly distributed, is there a simple test to determine how to weight them? Or does SPSS have a method to equally weight them? I think that it's not so much a matter of weighting unequal groups to see, and again, it may depend on exactly what you're doing, but for an independent variable, if you're just comparing two groups, as long as the groups are not severely unevenly distributed, so in your example, you say 120 males, 195 females. I mean, that is a little imbalanced, but not severely so. You can go ahead and still run something like a t-test to compare those two groups with each other. However, you just have to take into consideration that the greater degree of imbalance between the sample sizes of the groups, the less power your statistical analysis will have. So, and you can use something like G-power to determine exactly how that will affect the power of your analysis if you're doing something like a t-test, for instance. So I can just bring up G-power here as an example. So let's say that we're just doing something simple, like we're comparing gender, males versus females, on some kind of interval or ratio dependent variable. So we can do a t-test, and we can do difference between two independent means, two groups. And if we want to see the statistical power that we'll get if we know what our group sizes are going to be, we can do a post hoc power analysis. So we can look at our achieved power given our sample sizes. And let's just say we're doing this for a two-tailed test. And let's say we have this effect size of 0.5, alpha level of 0.05. And then here we can input the actual sample sizes for our groups. So in your example, you say 120 males and 195 females. If we type this in and say like 120 for group 1 and 195 for group 2, we can calculate our power, and we can see that, for just a t-test with two groups of that size, we can see we have pretty high power for that test. And we could maybe turn down our effect size to something smaller to see if that might affect the power. And we can see, okay, our power goes down if we reduce the effect size. But what happens if we make our sample sizes a bit more equal? So, with a low effect size and groups of these sizes here, we see our power is only 0.4. What happens if we make these groups more equal? And let's just say that we're going to take the same number of participants total, but split them evenly between the two groups instead. So if we have 120 plus 195, which is 315. If we split that evenly between the two groups, we get about 157 people in each group. So what happens if those groups were actually more equal to each other? So we do 157 in each group. So our total sample size stays the same, but this time our group sizes are more equal. We calculate that, and we see that our power goes up a little bit. But at a sample size this high, we see it's not really even affecting things that much. But what happens if we have something really severe? Like I said, if you have a very severe unequal distribution in the sample size. So let's say if we had, for instance, 120 in one group and only like 10 people in the other group, we can see our power goes way down. Our sample size has also fallen a little bit, but we also have a huge imbalance in our group sizes. So you can kind of use G power to kind of look at the dynamic of if you're just have something simple like two groups and you're concerned about the sample size imbalance, you can actually use G power to see how that precisely affects the power of your statistical analysis. Okay. And so I think that is all of the questions that we had. So I will go ahead and end our presentation here. Again, you can use this information on your screen to contact us in case you are interested in additional support beyond our webinars. And you also are welcome to look at the other webinars that we offer, because we do have other webinars on our schedule that cover different topics. If you're interested in attending another webinar that covers a different topic, you can take a look at what we have offered and look at our recordings of past webinars as well. Like I said, that's the end of our presentation today. Thank you everyone for attending. I hope this was helpful, and I hope everyone has a great day.